Okay, just while we set up, our next speaker is Ryotatsu Yanagimoto and Rajveer Nehra from Stanford and Caltech, respectively. And they're going to be talking about ultrafast nonlinear nanophotonics, a route to deterministic universal quantum information processing.
Hello. Oh, okay. So yeah, thank you for the introduction and thank you for the invitation to this wonderful workshop. So this talk has two parts. First part, I will give theoretical results, and then the other part is going to be taken care by Raj, who is going to give experimental prospects. Okay, so before I get started, I'd like to thank my collaborators across multiple institutions. Okay, so the main claim of this talk is ultrafast nonlinear photonics may realize deterministic or optical and non-Gaussian quantum information processing. This might be a bit of an aggressive claim, but the hope is that right toward the end of the talk, you find this claim at least not something a little more than a daydream, and that will be an ideal outcome of the talk. So this is really part of our attempt to push the boundary of what is possible using nonlinear optics beyond the scope of conventional Gaussian quantum optics into the non-Gaussian realm. Okay, so just as a brief introduction, I would like to note that optics is very good at carrying information, but it's not great at processing information, right? So optics has a lot of advantages as a carrier of information, right? And because of that, it is really an important backbone of our modern information society, right? On the other hand, also, right, it is arguably one of the only ways of establishing long-range entanglement, and also, because of that, people have managed to realize the largest entangled state using optical photons. And here, really the deal breaker in this context is the weak optical nonlinearity. Right? We want to do information processing, and we don't have enough nonlinearity. Right? So in the context of circuit, right, it's like we don't have access to the nonlinear circuit components like transistors. And it's obvious that there's no way of using such circuit to do useful information processing. In the context of quantum information, this translates to Gaussian operations, while nonlinear components are non-Gaussian operations. So really the lack of non-Gaussian operations in optics are the deal breakers in this context. Okay, so to define nonlinearity is a little more precise. What I mean by lack of nonlinearity is really the lack of single photon nonlinearity. So nonlinear coupling rate G has to be greater than kappa, to see some anything exotic in quantum. Right? So this chart is showing the achieved nonlinearity in nanophotonic platforms. Right? As you can see, we are still orders of magnitude away from all optical strong coupling, which is required to see non-Gaussian quantum physics. Okay, so then how could we even talk about optical quantum computation for the first place if we don't have universal gate set, right? The really innovative resolution was provided by Neil, Raframi, and Milburn in their seminal paper. The idea is to use nonlinearities induced by photon count. Right, so just to give you an idea of how it works, the rough idea is we have some Gaussian states coming in, and we perform photon counting on those states. And then depending on the photon counting outcome, it heralds the success of certain Gaussian or non-Gaussian operation, which might be, for instance, a generation of a GKT state, right? And really the nonlinearity or the non-Gaussianities are coming from these photon counters. And it is no exaggeration to say that I think more than 90% of the work in optical quantum computation rely on this paradigm, right? And I'd like to really emphasize that this is really the elephant in the room, right? The point is that it is realistic, but it has a lot of drawbacks, right? So the gate operations are inherently probabilistic, which is really tough for optics. And also clock rate is going to be limited because photon counters aren't super fast. Strictly speaking, this is not a room temperature platform. We rely on superconducting circuits, right? So it kills a lot of benefits of optics. And really like our hope is to propose a paradigm sort of beyond this use of photon counters. Okay, so the idea is pretty simple. Think about just using the natural dynamics of nonlinear. We encode some information in an optical pulse. It goes into some nonlinear waveguide, and then it induces some unitary. If this unitary is non-Gaussian, then we are good. This is going to be deterministic, can be operated in room temperature, and it is going to be super fast because this is just optical single path propagation. But here I'm expecting a lot of questions and criticism, right? Like, as I said, we don't have enough nonlinearity. Like, is it legal, right? And more subtle but more fundamental question is the multimode dynamics. Right, so nonlinear optical dynamics is known to be inherently multimode. This is really the deal breaker in this context, right? Like Jeffrey Shapiro made this super seminal paper titled single photon nonlinearities do not have quantum computation. The idea is no matter how strong the nonlinearity is, as long as we are relying on the single half propagation of the light, nonlinear dynamics, multimode dynamics is going to come in and bite us. And the final point, right? Even if we manage to resolve those challenges, what if those U is not useful, right? Like this U is nature given, so it's really like unclear if this is going to help us. Okay, so the hope of this talk is to answer those questions positively, which I hope is going to make a convincing claim towards this main claim of the talk. Okay, so let me get started from the first part. How do we enhance nonlinearity? A rule of thumb is we want to confine photons in a smaller space to enhance nonlinearity. Right? We can tightly focus the photons, but we can do a better job by using a waveguide, which gives tight transverse field confinement. We can do a better job by confining photons also in the temporal direction, which is achieved by photonic crystals, ring resonators, and so forth. But there's a critical trade-off between the confinement and the loss rate, and as a result, overall ratio of G over kappa is usually limited. The approach that we like to propose here is the use of ultra-short pulse. Right? Intuitively speaking, they are like flying cavities whose size is given by the size of the pulse. And as a result, we can circumvent this loss nonlinearity trade-off. So this is pretty qualitative discussions. But let me go into the numbers. Right? If you don't follow the numbers, there's no problem with that. Just want to point out that those numbers have been demonstrated at different places. So it's the purpose is to give you an estimate of the state of the art. Okay, so the type of nonlinear interaction that we care about is three-way mixing process. Annihilation of a B photon is going to produce two A photons, and vice versa. And loss rate, we assume 3D vanilla corresponding to 14 megahertz of loss. Right? And then the nonlinear interaction, we assume that the Hamiltonian takes this single mode form, where those operators are corresponding to the pulse degrees of freedom. Now, calculating the modal variable integral, we can calculate this nonlinear coupling, which is 16 megahertz. So to our surprise, we already have G over kappa greater than 1. We are in the strong coupling regime, right? Then it is really rigid, right? Really the subtlety here is it okay to assume single mode interaction? The point is, by using ultra-short pulses, we in principle have very strong nonlinearity, but really the deal breaker is the potential multimode dynamics, which is going to be the topic of the next part. Okay, so in an ideal world, if everything was single mode, then what is going to happen is two photons instantiated in A mode, they are going to up convert to this green photon over propagation. And then at some point, we see a perfect rabbi oscillation going on. Like there's no dispersion of the pulse. This is completely single mode, nice and clean. In reality, the Hamiltonian is really like nonlinear one-dimensional quantum field. So there's no way that we find single mode subspace within that. As a result, we expect to see some distortions of pulses, which really prevents us from operating a single mode, like a quantum dynamics. So really, if you do a simulation, it really looks messy. Okay, so the cause of the problem is the degeneracy of those degrees of freedom in this one-dimensional plane. Right? Like all those interactions basically kick photons around all the degrees of freedom in this pulse supermodes, and as a result, dynamics becomes highly multimode. A prescription that we like to propose here is the use of temporal trapping. Okay, so if we have some potential in this direction, it is going to form a bound state, and then this bound state is going to produce an energy gap from the rest of the continuum, which suppresses undesired nonlinear interaction. Right? Physically, what we can do is to have another optical pulse, trap pulse, causing this trap by a crossfade modulation point. Right, so really what's happening is for this multimode nonlinear waveguide Hamiltonian, we put these temporal trap terms, and it is going to confine the dynamics into a single mode subspace. So we do a numerical simulation, and as you can see, it recovers the single mode physics. So it's now we can make this number official because we know that this is a single mode interaction based on the same numbers. We get G over kappa greater than 1. So back to this chart, right? Using ultra-short pulses. We really think that it could be a way of bridging the gap towards the strong coupling by plugging in the more futuristic and hopeful numbers. G over kappa maybe greater than 550 may be viable. Okay, so this was the second part. And the last part of the question is, are we going to get useful dynamics out of this natural dynamics? And it turns out that the answer is yes. Okay, so in order to see how those non-Gaussian dynamics occur in nonlinear optics, it is insightful to think about this strange equation using some decomposition of a Hamiltonian into a Gaussian part and a non-Gaussian part. Okay, then what we do is to focus on the non-Gaussian part by factoring out the Gaussian part of the dynamics, which is going to leave us with a non-Gaussian part of the wave function evolving under the effective Hamiltonian. But as you can see, this effective Hamiltonian is produced by sandwiching this non-Gaussian part of the Hamiltonian with Gaussian unitaries. Right? So what it implies is that Gaussian part of the dynamics enforces some particular structure to the form of a non-Gaussian part of the Hamiltonian, which happens to make it useful for continuous variable quantum information. So to give you a more concrete example, let us consider optical parametric amplifier, but operated in this unconventional regime of non-Gaussian physics. Right, so the Hamiltonian is the same as the one that we considered before. And it turns out that we can realize a lot of interesting measurement functions, quantum non-demolition measurement of these observables have found to be possible. I can find the details in those publications. And these, an ability to perform such quantum non-demolition measurements are arguably pretty useful. The first function can be used to just replace the photon counter. Second function, we can make GKP states deterministically. Last function, we can do a cubic phase state generation deterministically, cubic QND interaction, and Heraldic state generation. So hopefully this gives you overview of how the non-Gaussian dynamics of nonlinear optics naturally gives us useful functions in quantum information. So I will go into a bit more details into those first two parts. Really, the idea of how these interactions come out of the natural dynamics of nonlinear optics is, let us start from the original Hamiltonian. But if you stay at the way how the Gaussian dynamics occur, it really happens under the squeezing Hamiltonian, because this is an optical parametric amplifier. We know in the classical domain, it acts as a squeezer. Right? So this is the Gaussian part of the dynamics. And if you stay at this form, in the presence of some finite delta, this looks like this is proportional to some photon number operator in a squeezed space. Right? So then in the phase space, it looks like squished quadratic potential. And this induces dynamics around those equal potential lines. So what it does is to enforce the dynamics to be projected onto the eigenbase of this Gaussian part of the Hamiltonian. So if you have a lot of Gaussian dynamics with some non-Gaussian dynamics, this Gaussian dynamics is going to enforce, project the non-Gaussian dynamics onto the eigenbases of the Gaussian Hamiltonian, which are squeezed photon numbers. And if you look at the way how the H effective looks like, now it takes a form that looks like an optomechanical interaction. But instead of a normal photon number, we now have squeezed photon number operator. Right, so let's see what we can do with that. We have this H effective, but then if you think about what it does, it really induces conditional displacement onto the B mode as a function of the number of photons in the A mode. Right, so if we use it in this way, then by performing a homodynamic measurement on the B mode, we can tell the number of particles in the A mode. Right, so this is really a way of performing a quantum non-demolition measurement of the photon number using an optical parametric amplifier. And as you can see, there's no photon counters involved in this picture. So we are using nonlinear optics to do photon counting. It's really a way of escorting the elephant out of the room. So the flip side of this nonlinear interaction is we can see a conditional phase shift induced by the, depending on the number of the amount of the quadrature in the B mode. And it is well known that this type of interaction can be used to generate a GKP state, actually deterministically using field forward operations. So by using this, we have also shown that using an OPA, we can get a GKP state deterministically out of a natural dynamics of nonlinear optics. Okay, so the hopefully those examples that have made a convincing case for this claim, all of this still are on paper. And for the rest of the talk, Rajveer is going to talk about experimental efforts that's taking place at Caltech, trying to make all those theoretical predictions into reality.
Can you hear me in the back? Okay. Hello, everyone. My name is Rajveer Nehra, and I'm a postdoc with Professor Alireza Marandi at Caltech. I would like to thank all the organizers for organizing this wonderful workshop. This is my second time. It's nice to see it grow bigger and bigger every year. So for the rest of the talk, I will talk about some experimental developments that we had at Caltech towards this goal. But before I talk about that, I would like to motivate nanophotonics in a scalability perspective. If you haven't seen this, if you haven't seen this setup, this is the Gaussian boson sampling setup from USTC team, and this is a theoretical experiment. It has a large scale interferometers where you have these bulky, discrete components that are precisely aligned and controlled. This is an impressive experiment, but it is my personal conviction that if you want to have a large scale quantum computer with millions of modes, we have to integrate all these bulky components on the single chip. And this is precisely what nanophotonic integration is all about. We want to integrate all the different components that we need for encoding, manipulating, and measuring quantum information for different applications. And if you do that, there are many advantages. For example, we'll have compact devices, and this would be an alignment-free setup. Once we couple in light, then everything would be propagated in the waveguide. We could mass produce this chip using commercial foundries. And finally, as you spoke about, that if we confine these optical modes in nanostructures, we can boost the nonlinear efficiency. So at Caltech, we are developing this emerging platform called lithium niobate. And over the years, it has made a remarkable progress because it has amazing optical, electrical, and mechanical properties on a single platform. So depending on what kind of architecture you are using, you could use all these different properties for implementing various quantum operations. So these days, you can buy these commercial wafers from this company called NanoLN. We could directly etch the waveguides on the thin film using standard e-beam lithography process. Here are some examples of our devices. And here we can see that the index contrast of these waveguides is very strong. So we can tightly confine both pump and the signal mode, which is what is shown here. The mode areas are very small. And because of that, we could afford to have very tight bands because the loss is going to be lower. And that would allow us to integrate a lot of these components on a single chip, which is what you would like to have for large scale processors. So before I talk about our results, I would like to give a general perspective of what is happening in this upcoming platform, lithium niobate nanophotonics. So we basically need three things. We need to generate quantum states, we want to manipulate them, and we need to detect them. So over the years, many demonstrations towards all these different components, they have been demonstrated, but all of these components are modular. So for example, in this one, we basically generated a squeeze state of light and measured that on a single chip, and I'll talk more about this work. We need to do route the photons over the chip. So, and if you want to do fast computation, we need very fast electro-optic modulators. So lithium niobate nanophotonics, we can use its electrical properties to fabricate and make these electro-optic modulators, which are more than 100 gigahertz bandwidth. And finally, we can also integrate SNSPDs and photodiodes for doing both Gaussian and non-Gaussian measurements on the same chip. So what's next? And the natural thing to think about is that we want to integrate all these different components on a single chip, and this is how it would look like. And if you're interested in doing continuous variable time-domain multiplexing, multiplex quantum computation, all these components that you need optical delays, you need some single photon detectors, you need some photodiodes, and then some nonlinear devices and electro-optic modulators. So all these different components, they have been already demonstrated by various groups around the world. So the particular device that we are making at Caltech is the phase-sensitive optical parametric amplifier, and this is a traveling wave device. So the bandwidth of this process could be tens of terahertz, so we are not limited by any resonance bandwidth here. And we could do it in lithium niobate nanophotonics is because we are using its second-order optical nonlinearities, which are orders of magnitude stronger than third-order nonlinearity of silicon-based platform. And there are some other properties that we could use to enhance the photon-photon interaction and also shape the properties of the kind of quantum state that we want to generate. I won't go into details about that, but these are basically different knobs that we can engineer using the fabrication process to develop different devices. So we fabricated a device, which is a 6 millimeter long OPA. And the first measurement we did was to just amplify the vacuum fluctuation to the macroscopic level. So what we basically do is we pump it with a 75 femtosecond pump, and we look at the signal using a classical detection. So in this case, it is basically an optical spectrum analyzer. So when the pump is off, we don't see any signal because it's a classical detector, and this is essentially the electronic noise floor of the detector. As we crank up the pump power, we start to see the macroscopic amplification of vacuum fluctuations. So these are like a lot of photons that we can generate just by amplifying the vacuum fluctuation. And using these generated average photon number, we can estimate the gain of our amplifier for the vacuum fluctuation. So this is the gain comparison in nanophotonics over different types of gain mechanism. And most of the devices are here, the traditional devices, the RP or the four-way mixing. This is where we are. So in 2021, we measured more than 100 dB per centimeter gain. And recently we pushed it to about 150 dB per centimeter. So this is an enormous amount of gain. And what can we do with that? So the first thing when we think about amplification comes to our mind is, can we measure quantum states just by amplifying them? Because we just amplified the vacuum fluctuations. So how do we measure quantum states? So, we need to amplify, we need to take macroscopic signal and bring it to the macroscopic level. So if you have a high gain phase sensitive amplifier, we could basically, and this amplifier is operating in the linear regime. So the pump is treated undepleted. And if you recall, this is essentially the squeezing Hamiltonian. So here, one of the quadrature is anti-squeezed or amplified, and the other quadrature is de-amplified or squeezed. So if you look at the average photon number after the amplification, it is given as this. And if you have sufficient gain, then we could directly measure the quadrature square just by measuring photons of the amplified quadratures. And this measurement is, it's essentially a sign-free homodyne. So if you have a homodyne detector, but you don't have access to the plus or negative value of the quadrature, this measurement is as good as that. But if you know that your state has a symmetry, reflection symmetry in the phase space, then this is an informationally complete measurement for characterizing those kind of states. You can do quantum state tomography. You could measure different types of non-classical properties of these kind of states. And if you're interested in measuring squeezing, we just need to measure the average photon number, which is basically the variance of the quadrature that we are interested in measuring. So an amplifier would generate and measure squeeze state of light just by operating it in a different regime. So we went ahead and made a chip. It has three main components. The first one is a squeezer amplifier, which is a low gain amplifier about 10 dB. And there is an adiabatic coupler that couples the squeeze state from here to there. And this is a measurement amplifier that amplifies that from microscopic level to the macroscopic level. And then we just detect it. If you want to think about that in the phase space, we generate 10 dB squeezing, which has about average photon number 2. And then if I'm interested in measuring the anti-squeeze quadrature, I simply set the phase difference to 0, and I further amplify the anti-squeeze quadrature, which is would look like this in the phase space. And then by comparing the variance of the anti-squeeze quadrature with the amplified vacuum quadrature, I can find out the amount of anti-squeezing present in the original squeeze state here. Likewise, I can change the phase difference to pi, and I amplify the squeeze quadrature. So this is a phase sensitive amplification. I can amplify any quadrature I want, measure the variance, and compare that with the vacuum variance. So this is the state of the art squeezing measurements in the nanophotonics, and most of these demonstrations are based on silicon-based platform. The squeezing has been limited to about 2 dB, but using these ultra-short pulse dispersion engineered lithium niobate OPAs, we were able to push this limit to 5 dB. And here I would like to emphasize that this is not because of weak nonlinearity. It happened because this adiabatic coupler did not come out as we designed it. So this was a fabrication imperfection, and we are trying to optimize it. So it was about 30% loss. But the important thing to note here is the loss after the coupling loss after the amplification does not affect our quantity measurement because we have amplified it to the mesoscopic level. All right, so what does it enable? In the near term, we are thinking about doing large-scale cluster state on the chip. And Warid gave a very nice introduction about generating these cluster state with these very complex optical setups. And it's pretty impressive that they have demonstrated tens of thousands of entangled modes. And in this experiment, the bandwidth of the squeezing is about 25 terahertz with 25 megahertz, which defines the spatial spread of the time bin. And it's about 10-meter long. So if you want to entangle hundreds and thousands of modes, then you need to use very long optical delays. And you can do that in free space setup using optical fibers or even free space delay. But if you increase the bandwidth from 25 megahertz to 25 terahertz, the nanosecond would become femtosecond, and your time bin would be 10 micron long. So we could integrate these optical delays with a centimeter scale on the same chip. So we could actually make the cluster state using these optical parametric amplifiers and also measure them using the amplifier. So this is quite exciting, and hopefully we'll have some results. But this is all about linear amplifier. This is all about generating Gaussian states and measuring them. But what we want to do is, as you spoke about, that we want to go beyond the conventional nonlinear optics in the quantum domain. So in this plot, what I'm showing is this is the measured gain, and these are different pump NSEs. And if you look at this carefully here, at one point you start to deviate from this conventional, the gain, where it will go exponentially in the linear amplifier, and we start to see some deviation. So this is where we are really entering in the nonlinear regime. And our goal is to push this limit to even lower photon numbers, so we could operate in the mesoscopic photons using these ideas of temporal trapping, and that will allow us to generate non-Gaussian states, for example, a squeeze cat. With that, I would like to go back to the claim, and I hope you are a little bit convinced that nonlinear, ultrafast, and nanophotonics could enable deterministic non-Gaussian quantum information processing. And with that, I would also like to acknowledge my colleagues at Caltech who helped with designing, fabricating, and making these devices. And with that, I would leave this summary slide, and I would like to thank you for your attention.
Thank you for the excellent talk. We may have time for 1 or 2 quick questions if there's.
So that was really neat. I only know microwaves. So can I ask, after the tuba, so after the optical tuba, OPA, is it really OPA?
Opa.
My grandpa. Okay, after my grandpa,
Yes.
you said something about the back action of these measurements. I think it was the slide maybe after this. So basically, we coherently receive. In that case, we think it like squishes phase-space, and then you do get negative and positive messages. You said you get like only Q squared because after you're putting like a photon detector.
Yeah, so we are measuring the intensity. After the amplification, we just measure the photon numbers.
And so then my question was, is that really safe from the environment? I know you amplified it, but the environment you can think of is also able to do a voltage measure. So do you still have problems that like you get Q squared, but somebody else gets Q? Does that have weird back action effects? I kind of feel like, at least for us, it would.
So you mean like someone just puts like some kind of reflector?
Put a
and
beam
then-
splitter after OPA and give some of the information to your enemy and have him measure Q, not Q squared. What does that do to the back action of the measurement?
That's actually a very good question. I'm not sure. Do you have an intuition?
Yeah, so I think what is going to happen is that this is really like you could have done homotime measurement and you can have got the same amount of that not evil person, right? So this is like this intensity measurement. It's like kind of forgetting about some of the phase information. Yeah, so I think your point is right that if we take out some of the light, right, like before the detector, somebody could have known the Q value and we could have got the same value. The point is, as soon as the signal goes through that amplifier, measurement is already done. The signal is classicalized. So it's like you can get as much information as you want.
Okay, maybe I could ask more offline, but.
So you could do a simultaneous measurement of, because now the signal is macroscopic, right? So one can measure Q, I could measure Q squared, and someone else could also measure QQ. That is true in principle, yes. Okay, yeah.
Can I ask a question about the first part? And you have this strong coupling region, right? Your G over kappa is a bit larger than 1.
Yes.
So could you comment on what would be the effect of the kappa for those later implementation when you want to do the case?
I see. Yeah, no, that's a great question. So it really depends on the type of dynamics we have. Like when we involve a very strong squeezing as part of this Gaussian dynamics, non-Gaussian dynamics, it does increase the impact of kappa because if you have larger quantum fluctuations, it is going to increase the rate of the loss. So I guess what we are finding here is around like the requirement is about the same as strong coupling, because if you think about the enhancement of nonlinearity due to the squeezing involved in the dynamics, like every operator gets amplified by the factor of a squeeze gain. Also, the loss is going to be amplified. So I guess really depending on the process, we sometimes get, I guess enhanced loss from this Gaussian part of the dynamics. But in some of the cases, right, like for instance, do I have a backup slide? I guess effect of the kappa. I think it's really a competition between the enhanced nonlinearity and the enhanced loss. In some cases, enhanced nonlinearity wins. And G over kappa, like 10 to the minus even 4, in some cases, we see negativities in the linear function. So I guess, the answer is, I think it depends on the type of dynamics that happens. Yeah, was that a satisfying answer?
I wonder, like, if you really want to create a good non-trivial like GKP state, what's the value of kappa over G that?
So GKP we found was a particularly hard task. We don't have an explicit number for that. We should have done a better analysis. I think we only did it for easier looking states. GKP, I don't think G over kappa 1 suffice for that purpose.
On demand.
I think for this type of photon number resolving QND measurement with a fidelity of say like 95%, G over kappa of I guess 1 was about okay. If we involve external Gaussian operations, we can push it even down to 0.1.
Just to add a point that you can actually squeeze the pump also along with the signal, and that would also enhance the non-linearity in the system. Yeah. I'm sure if you have that there.
Yeah, it's like I guess in addition to the original OPA, we can also think of doing like Hamiltonian engineering using Gaussian operations to really boost up the nonlinearities about another orders of magnitude. And with that, I guess the requirement of loss is going to go down a little bit.
This idea of raising the coupling by squeezing, usually there is also a problem with increasing loss.
Yeah, so that's an excellent question. I think in this paper we did analysis that even if you have some losses, is there a thing on the next slide there might be?
Oh yeah.
Or you can just go on this archive paper.
Yeah, but I think the idea is loss is going to increase, but nonlinearity is going to be increased a little faster because if you look at the nonlinear coupling rate, it is going to be amplified to the cubic of the squeezer gain, while the loss is going to go up as a square, right, like of the squeezer gain. So as a result, we win by a factor of R, and as a result, requirement for G over kappa effectively goes down.
And in principle, we can do these operations multiple times to even increase it further.
On. Okay, yeah, thank you very much for the very nice talk. So I have one quick question. So I think in your system where you have the OPA, so you use POM as in a way for your quantum state as well. So when you, for example, if you want to make quantum computer or information processing, at what wavelength are you planning to use? Like you're planning to use both the signal and POM for the computation, or how does it actually work? So
the idea is to see if we can see some non-Gaussianity for the signal and then use that as a resource to embed in the cluster state to do fault tolerance.
So I guess your core function, everything is still in the signal frequency,
That's right.
and the pump is just the kind of the ancillary for the non-Gaussianity. Is that correct?
That's right.
Yeah, I think something that we could also do is what's unique about this scheme is that your information is encoded in an optical signal instead of in an electric signal. As a result, right, this optical pump signal can still be reused. Right? We can cascade this process to do a non-local quantum non-demolition measurement. Right? As a result, this pump allows us to get some non-local quantum non-demolition measurement. So that's, I guess, another way of using a pump. Instead of measuring that, it's an optical signal carrying the result of your quantum measurement.
And another good instance is that this is a non-Gaussian entanglement, so you can actually use it to do quantum teleportation.
Everyone, please thank the speakers again and all the speakers in the session.